Today's lesson, we are looking at specific heat. So we're still playing with Standard 7, but now we're transitioning to Standard 7C, where we are going to be analyzing and interpreting specific heat data for substances to determine if they are insulators or conductors, to determine how much energy is released or absorbed, or even identify a substance's specific heat. So we're continuing our lesson on energy for Unit 2, starting with what's specific heat. So specific heat is defined as the amount of energy needed to raise 1 kilogram of a substance by 1 degree Kelvin. Can also be defined as 1 gram per 1 degree Celsius. But either way, we're looking at the energy needed to increase a specific amount of a substance, a specific temperature, and that's 1 degree. Remember, 1 degree Kelvin and 1 degree Celsius is still 1 degree. The lower the material's specific heat, the more the temperature is going to change when you add energy to it. So low specific heat items are called conductors. Substances with a low specific heat, that would be a small number, are going to be considered your conductors, and the lower the number, the better the conductor. Because it takes very little energy to heat that object up. So everyday example of specific heat, I'm sure especially in the summertime here in Georgia, you've had this happen where you'll go outside and you go to get in the car and you accidentally touch the seatbelt buckle. Well, that seatbelt buckle is made out of metal. Metals are really, really good conductors. That buckle is going to be extremely hot, probably well above 100 degrees Fahrenheit. My illustration here is saying 52 degrees Celsius. So now the seats inside the car, although they're going to feel warm, they're not going to feel nearly as warm as that belt buckle because the seats are going to be made out of leather or cloth or canvas, some type of a fabric that has a higher specific heat. That higher specific heat means it's going to take it longer to heat up. It's going to take more energy to change its temperature. So the metal in your car is going to heat up faster. The plastic's going to be kind of in the middle, and any cloth or fabric is going to heat up the slower of any of the substances in your vehicle. So specific heat, this is a calculation, has a nice, lovely equation. You are given the equation Q equals MC delta T on your formula sheet. So you don't necessarily need to memorize it, but they do not give you how to calculate delta T. So this is an equation that you want to add to your formula sheet. Delta T is calculated by taking the final temperature minus the initial temperature. And what that means is if I do this calculation and I get a negative Q, if I end up getting a negative value, that means my object lost heat. It gave up heat to something else. If I end up getting a positive Q, that means it has gained heat. It has absorbed energy from something else. Its particles are now moving faster because it absorbed heat. Now, for those of you who know you don't get along with algebra, let's plug this lovely little equation into our fun little triangle. Now, notice in my equation we are multiplying my 3 variables M, C, and T. M times C times delta T. That means we've got to show that multiplication in the triangle. So we're going to split the base of the triangle into 3 pieces instead of our normal 2. And in that base, we're going to plug in M, C, delta T. That means Q's got to go on the top. So if I was trying to solve for C, the specific heat of an object, I would have to take Q and divide it by mass times the change in temperature. So our nice handy dandy triangle comes in useful if you know you and algebra do not get along. And it works the same for any of the variables. It is important to note that you're going to always want to get your delta T value before you use your triangle. Otherwise, it may make the calculation a little bit more complicated. So let's look at a conceptual type problem for specific heat. I've got two samples of metal here. Not the best illustrations, but whatever. They both have the same mass. So I'm asking y'all which sample is going to take longer to heat. Well, we're going to come over to our data table. Frequently, specific heats are given to you in a data format, and you have to find the right one to use. So Al is aluminum. It has a specific heat of 920 degrees. Bad misreads. 920 joules per kilogram Kelvin. My copper, Cu is copper, has a specific heat of 380 joules per kilogram degrees Kelvin. I don't even have to say degree. I don't know why I am, but copper's number is smaller. The smaller the number, the faster it heats up. The larger the number, the slower it heats up. It takes more energy to heat up the aluminum than it does to heat up the copper. This is because they have the same mass. Now, that is only does it take more energy to heat it up, it's also going to take longer for that aluminum to cool down. Because whether I'm heating or I'm cooling, it's still only going to be able to move a specific amount of energy, and it's based on that specific heat. So it's going to take longer for the aluminum to get back to normal temperature than it would the copper. Roughly almost twice as long if you look at the values. So our lower specific heat means it's going to take less energy to be absorbed or released to change the temperature. And this is assuming that the mass is constant. I don't know why that word didn't stay on there, but it didn't. So assuming the masses are the same, the lower number is going to increase or decrease its temperature faster than the substance with the higher specific heat. Ooh. Okay, so now that we're done with the conceptual example, let's look at a calculation example. So in this problem, we've got, again, a word problem. Remember our three-part approach to approaching word problems? We write down our givens, we look at our equation, and then we set up and solve for our problem. So my givens, this first piece of information that I'm giving in the problem is 32 grams. Well, grams measures mass. So I know that that's my mass. The next piece of information I'm given is 8 degrees Celsius. That is my temperature. So we have two different temps to worry about, so we need to figure out which temperature is which, and that might mean reading the problem a little bit closer. So it says that we cool from 60 to 20. So from 60 implies that 60 is my initial temperature, and 20 is my final temperature. So my initial temperature is 60, my final temperature is 20. And it's asking us how much heat do we lose. So Q is my heat, and in order to use the Q equation, I have to know my specific heat. So even if it didn't explicitly tell me the specific heat, I would have to use a data table, kind of like we saw earlier, to determine that, hey, silver specific heat is 235 joules per kilogram Kelvin. So looking at my equation is Q equals MC delta T. It is asking us to solve for Q, so I don't need to rearrange it or anything. I don't have to plug it into the triangle. But I do want to solve for my delta T value before I try and plug it into my calculator. Because depending on the calculator, if I plug it in incorrectly, I'm going to get the wrong answer. Oh, now note that my unit for specific heat is kilograms, but my unit for mass is grams. our units don't match, therefore we're going to have to convert one to the other. In my PowerPoint, I converted grams to kilograms. So if you remember from middle school, maybe your physical science teacher used King Henry died by drinking chocolate milk. That was a mnemonic to allow you to convert from base units, which would be grams in this case, to other prefixed metric units like kilograms. In order to go from my base to my kilo, I got to move my decimal 1, 2, 3 places to the left. So right now, 32, my decimal's right here. 1, 2, 3 places to the left, and I fill in my zeros around my new location for my decimal. So that's how that 32 turned into 0.032. You're going to need to check your units. My delta T, in order to get delta T, remember, delta T is final temp minus initial temperature, and I did that backwards. There you go. So my final temperature is 20, therefore I'm going to have to take 20 minus 60. Yes, you're going to get a negative number, and that's okay. Now that I've gotten my numbers in more usable forms, I can actually plug them straight into my equation. I'm going to take my M times my C, Miss Rames, times my C times my delta T. Don't forget that negative sign. When you type it into the calculator should give you a negative value of 300.1. Remember that energy has the same unit as work. We got to have energy to go to work to buy our mom some joules. So the energy released, because that negative sign, was 301 joules. All right, second example problem. It's asking us what is the mass, and it's giving us joules, which we know is our energy, so that's my Q. And it's saying that my object heats from 20 to 90. So 20 is my initial temperature, and 90 is my final temperature. Lastly, it gives me my specific heat value. Specific heat is the only thing that we will play with that has this ugly of a unit, so don't fret too terribly much. So this time, I'm not being asked to solve for Q. I'm being asked to solve for my mass. So if I'm not good at algebra, and I cannot rearrange this equation to get mass by itself, then I'm going to take and use the triangle. Remember, this triangle is a little bit different than our normal ones. It has 3 spots on the bottom. 1 for M, 1 for C, 1 for delta T. So it is asking me to solve for mass. That means mass must be equal to Q over C delta T. My mass must be equal to Q over C delta T. That is the equation that I use. Now, I haven't found delta T yet, so let's actually go ahead and solve for that. So delta T equals T final minus T initial. So 90 degrees minus 20 degrees equals 70 degrees. Well, we heat it up, so it makes sense for me to have a positive change in temperature. Now that I've got my delta T, I can plug this into my equation. My mass is going to be equal to my 5,550 joules divided by my C. Oh, that was the wrong C. Copy and paste was not my friend. There you go. So 4,184 is my C for water. And my delta T was 70 degrees Celsius. If you're paying attention to 70 degrees Celsius, which is also equal to 70 degrees Kelvin, bad Miss Rains for not noticing that that was in Celsius. But 1 degree Celsius equals 1 degree Kelvin, so kind of nice. Still 70 degrees. But for those of us playing along following the units, notice that I've got a joule divided by a joule, and I've got a K on the side and a K on the bottom of another fraction, which means my kelvins are going to cancel out. And my only unit that I am left with is kilograms. Well, mass is measured in kilograms. Handy dandy calculator, plug it in. And my calculator gives me, the screen is not showing up too well, so let me switch to black. It gives me 0.018779 kilograms. So I know I've told y'all a general rule of thumb, give me 2 numbers after the decimal, but this is kind of a tiny number, so give me more than 2 numbers after the decimal. 3 or 4 is fine. You know, you could have put 0.019 and I would have been okay, but don't put just 0.02. You're losing too much by only giving me 2 numbers. So, think about what we've already talked about today. Substances that have a very low specific heat is a substance that makes a good conductor. So a conductor is any material in which energy can be transferred easily. It takes a very small amount of energy, very low inertia, in order to heat those objects up and cause the particles to move faster. Our conductors are typically substances that are solid metals because their molecules are really, really tightly packed. Their electrons are spread out in a sea of electron form, and it means that the heat, and of course electricity, but heat specifically, can move really, really quickly through that object. Gases and liquids tend to be really poor conductors of electricity. Gases, their particles are way too far spread out. They're nowhere near each other. Liquids, they're still touching, but there's a little bit of empty space between them, and they're not able to kind of transfer that energy as effectively as a metal solid. The opposite of a conductor is an insulator. So an insulator is a substance that does not transfer heat easily. It slows down the heat transfer. So your poor conductors are substances that take a lot of energy to change the temperature. They have a very high inertia in order to move the particles or change the particles' motion to increase it. What this means is we're looking at a high specific heat. Substances with a very, very large specific heat number tend to be your insulators. Examples of insulator, of course, the air in our rooms is a pretty decent insulator. Air is actually used as an insulator in some industrial processes, but other insulators that you'll probably encounter are wood or rubber. That's why many of our pots and pans have wooden handles or rubber plastic handles, because they do not conduct the energy as readily as the metal pot and pan. Summarizing what we talked about today with specific heat. So, the more mass you have of an object, the more energy you're going to need to heat it. Conductors are going to be substances that have a very low specific heat. They have small specific heat values, and they heat up faster. It takes very little amount of energy to change their temperature. Conductors are the opposite. So they have high specific heats. And because they have a high specific heat, it's going to take a lot of energy to change its temperature. It takes more energy to convert that to an increase in the motion of the particles and change the temperature. Now remember that energy is always conserved. It doesn't just poof, disappear. energy is going to be transferred from the object with the higher temperature to the object with the lower temperature. Now, insulators and insulations makes energy transfer slow down. This is why coolers and the insulation in the walls of your house and coats, things of that nature, help keep you warm, because they prevent your energy, your heat, from escaping to the outside, or they prevent the energy in the house, the heat in the house, from escaping outside when it's cold. That is it today. Remember, check our Google site for the corresponding assignments. Make certain that if you've got any questions, you are hopping into my open office hours and asking questions.